Okay, welcome back. This is 8.6. We're working with numerical integration, which is very important because there are integrals we're not going to be able to do by hand. If you look on the right, the book begins with that with this kind of issue. You know, you could usually always find a derivative, right? There's rules to follow, but for integrals, it's a little bit of a different scenario. There are some integrals that just don't have what they would consider an elementary antiderivative in terms of the functions that we know and love, like exponentials, square root functions, polynomials, rational functions, or compositions of functions, or rational functions built from those previously mentioned functions. Those would be elementary. So for example, very important integral, thing like e to the negative x squared over 2, which comes up in probability. This thing does not have an elementary antiderivative. Okay? So you're not always going to be able to do integration the way we've been doing it. You have to develop other methods, in particular numerical integration. Okay. You've kind of already done numerical integration if you remember in Calc 1 when you're developing the Riemann sums and taking the limit of those things. So that's kind of a basic way to do an approximation of the area underneath a graph. So recall what you did then. You would have left-hand rules and right-hand rules. Basically, the area underneath this curve could be approximated by a bunch of rectangles, right? So you can have a bunch of rectangles built with the left end point here. And you could add them all up and get an approximation of that area. So the sum of these little things, we'll call them delta A's, is approximately equal to the area under the curve. And then when you took the limit of that thing, you would actually get the integral, assuming some criteria were fulfilled. Okay, so you've kind of already done this, is what I'm saying. The only issue, the big difference now is you're going to be using different geometric objects. Okay, so what we're going to use first is the trapezoid, and so instead of rectangles, use a trapezoid. So now what this picture is going to kind of look like, and let me put it in a bit more detail. Zooming in here so we can see. I'm going to partition it up into a bunch of sort of intervals with the length change in x. I'll start at a, which is also considered x sub 0, and then go x sub 1, x sub 2, x sub 3, where the widths of each one of these intervals is change in x, and just, continuing on to some generic interval in here. So this would be x sub I minus 1 to x sub I, and then continuing on all the way to the end where we have x sub n minus 1, and then b, which I'll say is x sub n. Okay. So these, now we're not using rectangles. So what does that mean? The tops of these bars will be trapezoids. Okay, so you have the place where the left sort of line hits the graph, and the place where the right line here hits the graph. So you just connect the tops of those two lines with a straight line, and it becomes a trapezoid. Okay, so again, right here, maybe you can see it a little better. A straight line from those 2 points, that is a trapezoid. Jeez. Dropping a straight line, if I could draw that, and then you have a straight line on top there, and then this generic rectangle, or rather trapezoid here. Okay. And then this final trapezoid here. Okay, so in order to add all these up this time, we need to get a formula for the area of these trapezoids, right? Call it this area increment. So what is the formula for the area of a trapezoid? Over here on the top right, here I have the trapezoid object I'm kind of working with. It'll be this, the base we'll say is H, and then let's call this guy on the left, I don't know, let's call this H1 and call this H2 and call this H3. Okay? So the area of that thing is going to be 1/2 times H1 times H2 plus H3. So in our picture, this area increment, you know, what is that? The H1 is the base, so it'll be 1/2 times the base, which is change in x. And then H2 is the height based off of this left endpoint. So H2 then will be f, assuming this function, this graph is described by f of x. It'll be f of x of I minus 1, and then plus the other side's height, which would be f of x of I, okay, for my area increment. And then to get an approximation of the area underneath the curve, I just add all of those up, going from 0 to n. So I do this sum of the area, these areas, and I'm summing up from I equals, I guess, 1 to n. Right? So it would be f of x sub I minus 1 plus f of x sub I all over 2 times change in x. And we kind of have our Riemann sum here, and you take the limit, and that would equal the actual area underneath the curve as n goes to infinity. Okay. All right. So, right. We want to kind of expand this thing and make sure it's kind of look for a pattern, okay? Because we don't want to have to do too much work. So let's expand it and look for a pattern, okay? So the area, the sum of the area of these trapezoids, so we'll say, just write this sum thing again, sum of these guys from I equals 1 to n, that's going to equal, well, what is it in all of its glory, right? It'll be f of x sub 0 plus f of x sub 1. Please bear with me while I write this out. You don't necessarily need to write this out, though. All over 2 times change in x, and plus f of x sub 1 plus f of x sub 2 all over 2 times change in x. So you see there's a little bit of overlap between the expressions, so that f of x sub 1 is in both terms. And then plus, let's do one more, and then we'll go dot, dot, dot. Okay, plus f of x sub 2 plus f of x sub 3 all over 2 times change in x plus dot, 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 plus, let's put in, I guess, the last 2 maybe, f of x sub n minus 2 plus f of x sub n minus 1 all over 2 times change in x plus f of x sub n minus 1 plus f of x sub n all over 2 times change in x. Let's factor out the change in x over 2. Please note, what is change in x? So using this picture, change in x will be just b minus a all over n. All right? So if I factor out change in x and then do that substitution with b minus a over n, I'll have b minus a over n. Factoring out the 1/2 as well will give me b minus a over 2n. And then look what I'm left with. So I have f of x sub 0 plus f of x sub 1 plus another f of x sub 1 plus f of x sub 2 plus another f of x sub 2, and that goes on and on, right? And then plus f of x sub, we'll just go with the n minus 1 plus f of x sub n minus 1 plus f of x sub n. Okay? And this thing you can combine like these guys, right? So ultimately then that's going to be our trapezoid formulas, and that's theorem 5.17. Theorem 5.17. If f is continuous on this interval from a to b, the trapezoid rule is that the integral from a to b of f of x dx is approximately b minus a all over n times f of x sub 0 plus 2 f of x sub 1 plus 2 f of x sub 2 dot 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 plus 2 f of x sub, so there's 2 in front of all of them except the last one and the first one. Okay, great. So let's look at actually applying this to finding some area like they do in the book. Let's see if they have one for us. So sure, so, this is one we can do, you know, by hand, but because we can do it by hand, we can compare and contrast the answers, right? So example 1, we have the integral from 0 to pi of sine of x dx. So I can figure that out, right? It's negative cosine x from 0 to pi, which is negative cosine of pi is negative 1, minus negative cosine of 0, so that would be plus cosine of 0, which is 1. So my answer should be approximately 2 when I do my trapezoid. Okay. They'll tell you how many rectangles they want. Let's just do n equals 4. Okay. They'll also do n equals 8 in the book, but just for the sake of my sanity, let's just do n is 4. So let n equal 4, and then your change in x will be b minus a. So those come from the integral. So pi minus 0 all over n. So that's going to be pi over 4. And then if you want to, you can kind of partition your interval to kind of figure out how that's going to work, what values you need. So it's going to go pi over 4, 2 pi over 4, 3 pi over 4. And so those are the values that you're substituting into your trapezoid rule there from theorem 5.17, right? All right, so yeah, f of x is the sine of x thing. This guy right here is that f of x right there. So we're going to use that. Let's go at it, right? So the integral from 0 to pi of sine x dx is approximately equal to b minus a over n. That, you know, that's going to be change in x over n, which in this case is pi over 4 times 1 over 4. Sorry, there should be a 2 here. That's what I'm doing wrong. B minus a over n is just pi over 4. And then I need to put that over 2. Okay. So that's going to be pi minus, well, pi over 4 over 2. Okay. So pi over 4 for change in x and then divided by 2. It's the same as pi over 4 times 1/2, which is pi over 8. And what I just figured out is this part in theorem 5.17, b minus a over 2n. b minus a over n, again, is just change in x. That's pi over 4. And then all over 2. Or if you'd rather, pi over 2 times 4. You get pi over 8, right? Same thing. Okay, so I have pi over 8 out on the outside. And then you have to plug all of these into your function, f of x. So I have then f of, the first one, 0, plus 2 f of pi over 4, plus 2 f of 2 pi over 4, plus 2 f of 3 pi over 4, plus 2, oh, sorry, back to 1 then, right? So the last one is always 1. So 1f of pi. And then we can plug those into our f of x function, which is sine x. So this will be equal to pi over 8 times sine of 0 is just 0, plus 2 sine of pi over 4 is root 2 over 2, plus 2 times sine of pi over 2 is 1, plus 2 times sine of 3 pi over 4, where is that? 1 pi over 4, 2 pi, it's in the second quadrant, so sine is positive. That would be root 2 over 2. And then plus sine of pi is just 0 again. So you get pi over 8 times, this part will be root 2. This will be another root 2. So you get 2 root 2s plus 2. Okay? And you can simplify that a little bit. That'll be root 2 plus 1 pi over 4. Right, and you put that in your calculator, and the calculator will give you another approximation. This seems kind of silly, but so Wolfram, where are you? There you are. So root 2 of 2 plus 1 times pi over 4. That's about 1.89. So 1.896, the actual answer is 2, so it's close, right? It's relatively close. And of course, we get the same answers what the book got. If you take it up a notch, then you're going to have more points to evaluate, and you see they're doing it when n is 8. So that's the trapezoid rule. Down here they compare it to the midpoint rule. So the midpoint rule, you might remember, it would be another way of kind of doing your Riemann sums. So you could use left-hand endpoints, right-hand endpoints, or midpoints. And the midpoint would give you another kind of approximation. But we want to introduce some new ones. So the next one is called Simpson's rule. So section 2 here, Simpsons rule. And what we're going to do here is every 2 rectangles, we're going to kind of approximate it by taking the integral of the polynomial formed over those 2 rectangles with the points on the curve and the area underneath that polynomial. So let me kind of draw that out. So again, we have this curve. We want to approximate the area underneath the thing. And what I'm saying now is we're going to go by two sections at a time, right? So if you look at these 2 rectangles, there's 3 dots on the top. And what we're going to do is use a quadratic that goes through these points and use the area underneath that thing to kind of approximate the area underneath the curve. And we have to go 2 rectangles at a time. So in this case, you're going to have to always have an even number of rectangles to pull this off. So maybe another set here, and you'd kind of go like this and figure out the area underneath here. The first 2, you would be figuring out this area underneath that parabola, and so on and so forth, right? Dot, dot, dot. And then the last 2 rectangles, so to speak. And using those 3 dots, put another parabola under there. And we do this because the formula for figuring out the area underneath a quadratic is well known. You look over there, Theorem 8.4, they give you the area underneath a curve. So if you're going from, let's call this x sub 0, call this x sub 1, and call this x sub 2. So if you want to, and let's call this function f of x. So if you want to know the area underneath f of x from x sub 0 to x sub 2 dx, you can approximate it by finding the area underneath this polynomial, this quadratic, So let's say this red quadratic function here is p of x. Okay. So if you do the integral of p of x dx, it turns out that you don't really need to know the function to do that, because if you look there in Theorem 8.4, this is going to equal b minus a all over 6. So in this case, x2 minus x0 all over 6 times p of x sub 0 plus 4p times x sub 0 plus x sub 2 all over 2 plus p of x sub 2, right? And I'm saying you don't need to know the actual polynomial, because all you need are what the polynomial equals at those 3 points, and what the polynomial is going to equal at those 3 points is the same as what the function equals at those 3 points, because we're specifically choosing the polynomial to go through those 3 points. In other words, you can evaluate this integral of this polynomial just by evaluating f of x at those points. Whoops. Those will have the same answers, right? And that's kind of the basis for Simpson's method. And if you were to do the same sort of exploration that I did with the trapezoid method, where we kind of then found the sum and expanded the thing, as you see, did they do it? No, they didn't really do it. But if you were to be ambitious enough to find the sum from x sub 0 to x sub n, so the whole sum, and then expand it and look at it, there's going to be another grouping issue where you have, or bunching issue rather, where you have 2 terms kind of bunching up on each other. In particular, it's going to be, if you look on the right, where you have, or I can show you online, when you add them together, there's going to be an f of x2 right here, and then your next sort of expression would be f of x sub 2 plus 4 f of x sub 2 plus x sub 4 all over 2 plus f of x sub 4, and then you would get the bunching happening on this f of x sub 2, f of x sub 2. So the Simpsons rule, the formula for it then, and Theorem 8.5, again, we assume that f is continuous. The integral from a to b of f of x dx is going to be approximately b minus a all over n, the change in x, but then you factor out a 1/3. We're actually, you just have to do some algebra and stuff, but you'll get b minus a over 3n, and then times all this stuff, the f of x sub 0 plus 4. So you see you have a coefficient of 4 on here. 4, and the reason why we had 6 here is because we just had 2 rectangles. But if I add in this other stuff, then we have more rectangles. But this was just hopefully just kind of explaining to you why there's the coefficient of 2 that's coming up here. But 4 times f of x sub 1, if you make the widths equal distance, the midpoint of x sub 0 and x sub 2 would be x sub 1. And then the bunching happens, so there's going to be a coefficient of 2 on the next term. Then you have f of x sub 2, and then plus 4, f of x sub 3, and then that pattern continues until you get to the end, and you always end with 2 and then 4, f of x sub n minus 1, and then plus just plain old f of x sub n. So the book will make a big deal of the patterns involved. So 1, 4, 2, 4, 2, 4, blah, 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 4, 2, 4, 1 is the pattern. And it's caused by the way we've built the this technique. Okay. All right, so that's theorem 8.5. Let's apply it to so, whatever problem they picked for us. One move, please. Oh, that's error analysis. I don't want that. Oh, they want you to do the same one. Simpsons. Okay. Let's do one that we can't do. Okay, just for the sake of doing something interesting. Do I include? No. So let's see if we can actually get an approximation for the integral from, I don't know, 0 to 4. We'll use n equals 4. Or let's use n equals 6. Let's at least go up a little farther. And we'll do the e to the negative x squared thing. That's not integrable for us. So anyways, the formula, it's change in x basically over 3. The change in x is going to be 4 minus 0 all over 6, which is 2/3, unfortunately. And then change in x over 3 is going to be 2/9, unfortunately. So the points we have to work with, we're going from 0 to 4, we're going by 2/3. So 2/3, 3/3, 4/3, 5/3, 6/3, 7/3, 8/3, 9/3, 10/3, 11/3, and then 12/3. Okay, so we got a lot to do apparently. Shouldn't have picked that many. That's not 6, is it? It's not 6. 4 minus 0 all over n. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's see, 11 sections. So 4 minus 0 is 0 all over n. Number of rectangles. Should be 6. What the heck did I do wrong? 2/3. Oh, the change in x is 2/3, not 1/3. Oh. So 4/3, 6/3, 8/3, 10/3, and then 12/3. So just those, and then 1, 2, 3, 4, 5. Okay, here we go. Right, so I got 2/9 times, this thing evaluated at all these numbers. So f of 0 plus 4 f of 2/3 plus 2 f of 4/3 plus 4 f of 6/3 plus 2 f of 8/3 plus 4 f of 10/3 back to plus just plain old f of 12/3. Okay. Then I plug those all into my f of x, which is this dude right here, and I'm going to type this into Wolfram. Hopefully I can do some copying and pasting as well. So what is it? It's 2/9 times some big mess. So each term will be e to the negative something squared, right? And then, okay. So I'm going to copy that. Plus 4, plus 2, plus 4, plus 2, plus 4. Is that all of them? How many did I need? 1, 2, 3, 4, 5, 6, 7. No, it didn't. It did. I don't even. Really? 2/9 times e to the negative something squared. Okay, so that will be plus 4 plus 2 plus 4 plus 2 plus 4. So that's 1, 2, 3, 4, 5, 6 plus 7. Okay, and now I need to go through and plug in these numbers. So it'll be 0, 2/3, 4/3, 6/3, 8/3, 10/3, 4. So it's saying 0.88 something. I'm almost afraid to touch over here, so it'll go away. 0.883 Okay, great. Let's see what it actually is. Well, first off, let's just look at the antiderivative. E to the negative x squared x see they need an ERF function. If you take Calc 3, you'll be able to kind of figure out how to get this answer. Or actually, you need complex numbers, I think, polar stuff. In Calc 3, I think you should be able to do that. But for right now, we can't do it, right? So let's figure out what the actual answer is from 0 to 4. Yeah, 0.8839, 0.8862. So we're pretty close, and hopefully that convinces you, yeah, we kind of need these other methods because we're not going to be able to integrate things like this. Okay, let's see if they have any other sort of issues we need to deal with before we call it quits for the day. There's some error analysis stuff. I'm not going to go into that. It's all very interesting. You can read it if you want, but I'm going to skip that part. You don't think I put it in the homework either. Let's take a look. Yeah, I don't think I put it. Well, I didn't give you a video quiz, so let's go to the homework and pick out a video quiz problem for us. So we're in video quiz set number 5. This will be the second problem in that set, and let's make sure there's no error stuff in here. There's no error analysis. Let's try number 7. Okay. And see how that goes. So this is the video quiz then. Move this over here. Okay, so I want the integral from 0 to the square root of pi. That's not annoying at all. Pi over 2, and then sine of x squared dx, right? So first, note they want n equals 4. They want you to do trapezoid Simpsons and then just evaluate it using Wolfram or something. So anyways, your change in x is going to be square root of pi over 2 all over 4. And, jeez, bunch of jerks. So if you look at your interval, that's going to be 0, and then square root pi over 2 all over 4, and then 2 square root pi over 2 all over 4, and then 3 of those, and then you're up to 4 of those, so square root pi over 2. First we'll do trapezoid, so trap is going to be equal to the number that goes under is 2, so it's change x over 2, so for us that would be pi over 2 all over 8, and then we want f of 0 plus 2f of that thing, and then plus 2f of the next thing. This is over 4. So 2 of those over 4 plus 2f of the next thing. And then plus just the 1 f of root pi over 2. Okay, I'm going to go to my calculator then and just plop that in basically. Alright, so square root of pi over 2 divided by 8 star a bunch of junk. So what do I need? Sine of this first one's going to be 0. Putting sine in there. And then it's going to be plus 2 sine of this thing squared. So it's going to be pi over 2 over 16, right? So pi over 32 plus 2 sine of pi over 2 times I just so do not feel like thinking. You know? So the first one is, so this guy, when I square it, is going to be pi over 2 times 1 over 16. This one is going to be pi over 2 times 1 over 4. This guy will be pi over 2 times 9 over 16. And the last guy will just be pi over 2, I'm hoping. Yeah. So I'm on, which one am I on? The third one. So it's pi over 8 plus 2 sine of 9 pi over 32. And I bet they want a multiplication symbol in here. Plus, and the last one, I think, sine of pi over 2. And I'm getting some crazy number. 0.54 niner. I don't know how many decimals they want. 4. 5495. Usually what I like to do is just see if it works in here, and then I'll go on to the next one. I don't think it marks it wrong if you don't put anything in there. I just want to see if that's right before I carry away. Let's get the actual answer here. So going from 0 to square root of pi over 2. function, though, is sine of x squared. Right. So the actual answer is even close. Yeah, all right. 0.5493. And then go for Simpsons. And I think Simpsons, you can just replace the coefficients, right? So for Simpsons, it's basically the same thing. Oh, and you need a, so before, for trapezoids, the denominator is times 2. Now the denominator is times 3, so this will be a 12. But you can kind of just edit what you already have by changing the coefficients, right? So it'd be 4 blah, 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 plus 2, blah, 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 plus 4, blah, 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 plus 2, blah, 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 plus 4, blah, 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 plus f of, whatever, right? So let's go and do that. So I have to change the 8 to 12, and I have to go through and change these coefficients. So if you're doing computer programming, I mean, you could write up the code and then just hit enter all the time and have your answers. I'm not that advanced at computing, doing code and stuff. But anyways, 0.5483. Let's see if that's right. 0.5483. Drum roll. Yay. All right. So as usual, thank you for watching, and I will see you next time.